Okay, go ahead.
I put in silence all the microphones just for security reasons. Okay. Okay, good morning, everyone. Good afternoon for those that are in Europe. Today we have the presentation of Professor Frede Blaabjerg, a full professor from Aalborg University. His research interests include power electronics and its applications such as wind turbines, PV system, reliability, harmonics, and speed drives. He has published more than 600 journal papers in the field of power electronics and its applications, and has received a lot of prize papers award from the IEEE, including also the Villum Rasmussen Research Award in 2014 and the Global Energy Prize in 2019 and 2018 IEEE Edison Medal. He has been also the editor-in-chief in the IEEE Transaction on Power Electronics, a distinguished lecturer for the IEEE Power Electronics Society and Industrial Applications Society, and also he served as a president of the IEEE Power Electronics Society between 2019 and 2010. He is nominated in 2014 to 2020 by Thomson Reuters to be between the most 250 cited researchers in engineering in the world. Professor Frede Blaabjerg, thank you very much for accepting our invitation. And now the microphone and the screen are yours.
Okay, thank you. Thank you very much for the introduction and also the invitation to come here today and give a presentation. Let me see, I'll try to share my slides here. Let's see. Is that fine?
Yes.
Super.
Yes.
So my topic of today and in general also during my whole career have been the power electronic technology where we do the electrical energy conversion in a smart way, efficiently, and with lower and lower cost, and in that way be able to let's say, create what we will call the modern carbon neutral society. So I hope you'll get some inspiration from this. So I will give some overview about this topic. Then I will discuss a little bit which kind of conversion are we applying when we are heading towards a carbon neutral society. And then at the end, I will make some heads up in terms of challenges and also do finally some discussions what to be looked at in the future. Just a few words from where I'm sitting now. You are down here, right? I'm just at the opposite. We have now very nice summertime, very light days up here in Aalborg. Let's take this one here. Yeah, I'm located up here. It's a long distance from your place. Anyway, I guess you have a winter time now. But up here, Aalborg and Denmark is this part here is a small country with around 6 million people. Over here is Copenhagen. Up here we have the city of Aalborg. And Aalborg University is university, full university with 22,000 students, and we are 50 years old. And what I can say is that we are based on, let's say, another teaching philosophy compared with traditional. We work all the time in teams and do problem-based learning in our way. So our students, they learn to solve problems. But my topic of today is a little bit as the carbon, as a carbon-free society, and which means are taking in order to go into that direction, and how can we help with that, seen from a power electronic perspective. And let me just initially take this slide here, because I think this is a slide indicating the global sustainable development goals, which I think is really one of the right directions to go to set up some common goals for the world in order to ensure that the world, the planet, is worth to live on. And there are 17 different areas where some of them are really on the basic things like no hunger, good clean water, you know, all the basic things. But of course, also, if we think about a modern society, we really need energy in order to, let's say, to create prosperity, create easier way of living. And that is also something which the Sustainable Development Goals see as a very, very important aspect. And one is renewable energy to go for that. It's also about sustainable cities and communities that we should really strive towards this. It's climate action, really to do something towards reducing the carbon emission to the out in the the atmosphere. And there are also other aspects here which I would say gives very good arguments for looking at how to that we are really trying to reduce carbon emission. And here you can see some of the plans, because you saw one of the areas was climate action, right? And there is no doubt that it is the case that the Earth is becoming warmer and warmer thanks to the emissions from let's say people like you and me. And if we really want to be sure, if we should have a chance on a long run, then we have to do something about this carbon emission. If you see here, and one of the absolute main reasons are the energy supply, which today, as you can see here, is coming mainly from oil, natural gas, and coal. Part of it is electricity and biomass, but you can see it's really very much fossil fuel based. And one of the organizations meaning something in this area is called ENER, and they have tried to predict what can we do in order to limit the temperature rise on the planet to only be 1.5 degrees C compared with today. And the way to do this is really to transform the energy supply from being fossil fuel based to be much more renewable based, where the overall infrastructure now is electricity based with more than 50%. And of course, just imagine the car areas, but also modern biomass, hydrogen, which is also done by electricity when we are doing such kind of things, but other renewables, district heat. So to fulfill what we can say the sustainable development goal, to do something with climate action, we need to transfer our energy supply. Also, what you should remark here is that there are in this transformation, also an efficiency improvement, for example, due to that the automotives, they are becoming electrical based, and this is much more efficient compared with applying oil, coal, and natural gas as such. And if we look at the energy system, we have here power stations generating electricity, but also waste heat, which can be applied. we have a transmission, a distribution, and then we have efficient use of electricity. And the renewables, you can see here, wind turbines, photovoltaics, maybe also the fuel cells, including storage. And what we see more in a system like this is that we have electrical vehicles, or we have plug-in hybrid electrical vehicles, which also are playing a major role in the whole energy system. And if you look here, we are applying power electronics to do the conversion of electricity from one form to another, and in that way control the process either through production or through consumption of energy. And one of the very important aspects is, of course, renewable generation, where here you can see the installed capacity over the last 20 years, going from 800 gigawatt to close to more than 3,000 gigawatt today. And the main increase, you can see this has been happening in the renewable, which are the solar and the wind energy. Seen from a market perspective, every year you can see here how many gigawatt it is year by year. In 2001, only maybe 10 gigawatt, but now in 2020 is 250 gigawatt, where absolutely sun and wind are the dominant one. You may then ask, okay, is that a big part of the whole generation, new generation? And this is illustrated, that could be illustrated, but this is around 80% of all new generation capacity. If we look at wind power, which is one of the important part of the whole story, you can see here the installed capacity in 2021. It was around 100 gigawatt, but this has been steadily increased in the last 20 years. And what is really amazing to look at here is the size of the technology, where to the left you can see how the size was in 80. In 2000 it was 40 times bigger. And now in 2020, or 20 years later, it's even 7 times bigger. And now we are looking into turbines with a size of 15 megawatt. Looking at, let's say, the size of the blades is really amazing, going from a diameter of 15 meter up to a diameter of more than 200 meters today. What is important to have in mind here is that the interface is done by electrical energy conversion as the power electronics technology. So we can control the speed of the turbine, and we can control the power we are feeding into the grid system in a proper manner according to the demands. So in the beginning, we did not really apply a lot of power electronics electric conversion to connect the turbines to the system. But today we are really applying a lot of power electronics. If we look at the photovoltaics, which was the other one, which is really increasing a lot in terms of installed capacity, we can say that we have a huge number of different technologies which can fundamentally be applied as where we have sun, we have irradiation, and then we process it in a panel, and then we get DC out, right? And we have here maybe 20 different technologies where the highest efficiency is close to 50%. We have some which are very low, but what is often the case here is that the efficiency, the cost to manufacture is very low, and that makes it very cost efficient. If we look at the installed capacity here, you can see this has only been extremely rapid in the last 10 years. And I think the main reason is that we have seen production capacity enabling the possibility to lower the cost. So the cost is really, really reduced compared with, let's say, 10 years ago. And we know that in order to do this, we need to process from DC to AC so we can connect it to the grid system. But let me also then highlight one of the challenges we have in general. That is that for a good number of applications, we can say that we are really not able to fully electrify it directly because, for example, in airplanes and others, it's very difficult to get a very high energy density. So what is really being looked upon is to have, let's say, an intermediate stage of making hydrogen in order to get some of the products from the fossil fuel. And this is, of course, let's say, the oil in general. It's but also part of heavy trucks for mobility, but also the chemical industry is a part where we need something to substitute the oil. And if we look at that, in order to do that, of course, we need the power electronics. You can see here to the left to do the power processing for generation, but we also need the power electronics for doing the electrolyzing. And maybe even later on here, we also need power electronics in order to process and to be able to get the different, let's say, products out of the hydrogen. So again, this is achieved by applying power electronics. And what we now see for very big projects in order to offer this possibility is to build, let's say, centers, production centers. It could be onshore, for example, also in Chile, PV and so on. And in our case in Denmark, in energy islands, that we call them, where we are feeding, having a different wind power plants connected like this. Then we do an artificial island or two, where we gather all electrical power together. On this island, we could do the processing of the power, so we do not have to transmit the electrical power onshore, but we could also do it. Or we could, let's say, do the power processing on the island in terms of creating hydrogen or something after that, and then have a pipeline to feed the power into onshore. And then, of course, this gives a lot of flexibilities in order to be connected with other centers where we can exchange power dependent on the processing. But all those things, again, is enabled by large-scale power electronics in order to be able to deal with, let's say, the intermediate nature of the renewable. Some words about how we are doing this then, and seen from a processing perspective. And yeah, what we really, the way we do it is, of course, that to the left here, we have the generator. To the right, we have the grids in most cases. And in between, we are applying, let's say, our components, our controllers, and so on. And then we do some software in order to be able to process the power from the generator to the grid side, and maybe also we need some communication. But this is really what power electronics is about: doing the electrical conversion, control processes at both sides, and do this in a way so we have security of supply. Cost should, of course, be as low as possible, efficiency as high as possible, and then a lot of controllability actions in order to ensure that we have a reliable system. And that also, of course, also includes that the hardware we have been doing has a standard which are not disturbing, let's say, other systems in that respect. If we look at for the wind turbine system, just as one of the important cases, we can say that for the wind turbine, what we need to do there in order to control the speed of the generator, we need to have a wind power conversion system where we can control frequency and voltage in order to control the speed. And then at the other side, we need to control frequency and keep that fixed at 50 hertz, or at least just follow what's going on the grid side. And then the voltage, which is also fixed. And in between, we have the power conversion, which should all the time try to have a, let's say, an energy balance between what is demanded to the grid and what is coming from the generator. It should also have a high power density in order to lower the weight, because we are putting the converter in the top of the nacelle, and of course also high reliability in general. And the way we, let's say, realize this part is illustrated here. We can either do it with a double-fed induction generator system, where the stator is connected to the grid, and then we have a converter dealing with the power from the slip rings, from the rotor side here, and then have an AC/DC and DC/AC converter in order to realize this by the power electronics. So if we have that, then we are able to adjust the speed around the synchronous speed given by a three-phase generator here, let's say plus minus 30%, and then the size of this conversion is only 30% of the whole turbine size. It has the disadvantage that when we have some issues on the grid side, voltage fluctuates, then we will also see that at the generator, and we need to take care. The alternative is this one here, where we have a three-phase generator. Then we, to the right, have the grid. And here we do AC to DC conversion, where we convert the full power. And here we do DC to AC conversion, where we also convert the full power in order to, let's say, feed the power into the grid. But this has the clear advantage that we can decouple almost the two systems. So we can, if something happens at the generator, we can decouple the grid, and opposite, if something happens at the grid, then we can decouple the generator and try to deal with that. Here are some of the technologies we are applying. Typically, we differentiate between low voltage, medium voltage, low voltage. It's a back-to-back converter, where we have a converter here, three-phase, to control frequency and voltage for the generator, and three phases controlling towards fixed frequency and almost fixed voltage to feed the power into the grid system. If we have a wounded rotor or on the synchronous generator, or the generator is able to generate a back EMF, then we do not necessarily need to have an active converter here, but then we can just do a rectification here by a boost converter and then a diode rectifier in order to achieve the performance we need. But otherwise, to the grid side, we have some of the same things. For the converters for the photovoltaics, which is of course also important, we are dealing with from hundreds of watts to fundamentally gigawatt, we can say, where we have DC to this side, where we should extract the maximum power out of the panel, and then we have the grids, where we have constant voltage and constant frequency. What differentiates this technology a little bit is that typically this is placed outside, while the nacelle, as the wind turbine, the converter is placed inside the nacelle of the wind turbine. So there are some, let's say, outdoor issues we need to deal with, for example, temperature management, humidity, and in that way also, of course, try to get high reliability. What is also a demand typically for this kind of technology is that it should be able to detect if the grid is disappearing, because otherwise there's a risk that this one here can operate like a real grid without detecting it or something like that. So there should be some islanding protection. And here you can see the different ways of realizing the photovoltaic technology from a converter per module. You can see here either with two states or one state. Here you have a DC converter per panel, and then you have a DC bus and then DC-AC. Here we have a string system. Here you have multiple strings, which we see a lot for the larger scale systems. And then we have here a central inverter, and they have pros and cons. And of course, the big ones we are only applying in big plants. So here you can see the different ways to realize this. Those systems here, we can do it with galvanic isolation, without galvanic isolation. If we have galvanic isolation, we can do it with low frequency and high frequency transformer. If we if we are not having any galvanic isolation, then truly we have a DC-DC and then a DC-AC conversion, where the challenge for doing it transformerless is that the voltage is jumping up and down, and we need to deal with potential ground current because we have a very big area of this panel, and because if the potential jumps up and down, then we can easily have capacity coupling to the ground, and we need to be able to take care of that. Here are some of the, let's say, transformerless inverters. The reason we go for this is we save magnetics, we save weight, and we can have high efficiency. And here you see 3 different converters which are very accepted in terms of string systems with high efficiency and also a big controllability possibilities and so on. An H5 transformerless inverter, H6 transformerless inverter, and then I would say this one is becoming very popular, a neutral point clamp converter, where the requirement here for the filter is not very high. So this is a very popular way of doing the DC to AC conversion. And then if we go up to the big systems with many arranged central inverters, like you can see here, we go from low voltage to medium voltage, and then from medium voltage to high voltage. But as I told you, this was a generator. Then we also have more to the consumer side, and I would say this is really booming a lot. So how are we going to make the hydrogen in the future? It's booming, like we have the big data centers and so on. And the thing with the making the hydrogen is that we need DC, and every percentage we can increase in efficiency matters really, because those systems here have to be operating for, let's say, 8,000 hours if possible. So here you can see, let's say, size. Typically we will see those systems, and the challenges are in general low cost, scalability, and of course reliability in general. And here are for the big system some of the solutions in order to do that. There are pulse as a coupling of let's say thyristors and transformers in order to ensure that we have a low cost but high efficient system, and then at the same time also have a good TS as a power quality performance at the line side. Here's another solution where we are using an active filter in order to create a very good power quality at the line side. You can see some numbers here, but this is one of the lowest cost ways to ensure that this electrolysis has a cheap approach in general. But there are also other ways of doing those things, and that is not having thyristor, but then have let's say buck converters to control the power into the electrolyzer, and then still apply a 12 pulse transformer, which gives a relatively bulky system, but it is a very proven technology for a huge number of power when we are dealing with it. And another solution then is, instead of having a rectifier here, then we have an active rectifier here and here, and that gives a very nice power quality in general, very high power factor and so on. And it also gives very good let's say performance into the system. But of course the components numbers are high, and there are also let's say some bulky components still in this situation. And then there are other ways, of course, to look at this in order to make the hydrogen medium volts or low voltage, and apply what we can call a modular multi-cell rectifier, where we can achieve a very high TSD, high redundancy, and we are not needing in those situations here, let's say, a very bulky transformer in order to ensure that we have a good enough performance. But on the other hand, looking at the component counts, they are relatively high. Okay, let me end my presentation to look a little bit on the challenges and do some discussion. One of the big things are, of course, the reduction of carbon emissions seen from a global perspective and also according to the Sustainable Development Goals. And in Denmark, we are really moving fast ahead. This is where we were in 1919, and this is where we are, and we really want to go way, way low in 2030. And what has happened is we have really changed the energy system from being a few components producing power to many components producing less power, but in total they produce the electricity we need to do. And that means we have changed our energy power structure from being a few rotating mass systems to be a lot of units with power electronic as the interface. And we have tried to, let's say, gather, such a big synchronous generator, gather that together through wind turbines, and in that way have a wind power plant, which is acting like a very big synchronous generator. But of course, what that gives us when we are basing everything on the let's say renewable is that we have something which are weather dependent and seasonal dependent to a large extent. And we have to look at how we are ensuring that we are able all the time to provide energy and power on demand. Some of the solutions have been a little bit around. You can see here the variability, for example, during one day for PV, and of course you also have that in Chile. But some of the ways to ensure such kinds of, let's say, storage is, of course, for example, to put it into hydrogen and do something, or batteries, or play much more together with some of the other energy carriers like heat and gas system, in order to be sure that we have a very robust energy system. And what we of course need to do when we deal with all this technology is to look at how to reduce cost of energy. And here I will just highlight what is cost of energy. Cost of energy is the capital cost, the operational and maintenance cost divided by the annual energy production whatsoever. And what you can see here is that if the reliability is poor, then we are not having the production we want to have. So this energy will go down, and the operation and maintenance cost will go up. So we are double punished if we are not doing a reliable system. And here are, let's say, some of the demands which are important to look at in order to design our equipment towards what is needed. Here you can see different sectors of application: aircraft, railways, maybe 100,000 hours, industrial motor drives, maybe 60,000 hours, automotive, maybe 10, 15,000 hours of operation. And then you can see the renewables here are demanding at least 100,000 hours and maybe even up to 150,000 hours, because we want those here to be able to operate more than 20 years or 30 years in order to use as much as possible of the investment of making the products. So this is quite interesting to look at. And what is really moving very fast in that respect are the component we are applying in the conversion of the electricity, where we see a very big, let's say, change from silicon devices to wide bandgap devices. The wide bandgap devices are based on material which are extremely powerful in terms of switching performance, much better than silicon. So we have new devices which are maybe 10 times better than the silicon devices for high voltage, for example, based on silicon carbide. And we have for the low voltage gallium nitride, which are over competing a lot of performance we have seen in the before. So this is really interesting to follow, and I'm sure also many of you, if you are working in the electrical engineering domain, will see that the progress here is fantastic. And then I will also highlight that the total change of the transportation sector from going from being a fossil fuel. This is very important in the diagram you saw before, to become electrical based. We can only do this with a huge number of power electronics. So what you have here is a vehicle where you have to do a drivetrain by power electronics. You have to have a battery which is controlled by power electronics. You have to charge the battery, which is done by power electronics. You have to have auxiliary power, which is done by power electronics. So everywhere we have power electronics in that respect. And if we look at what are the demands for the technology, we have maybe 300,000 kilometers of operation, which is going to be 600,000 kilometers in the future, and then an active operating time which will be moving from 8,000 hours to 36,000 hours in a situation where we believe more on autonomous cars. And there are huge specifications for the power electronics there in the future to lower cost and of course also have a high reliable system. So this is hopefully giving you some, let's say, insight in the role of power electronics to, let's say, to develop a carbon neutral society, both in terms of generation, in terms of consumption, and some of the big challenges we have in terms of the high energy density application like airplanes that we need to do hydrogen, as well as also the transformation of the transportation sector from being fossil fuel based to become much more, let's say, electrified. And if I should draw some conclusions today, solar and wind, in my opinion, are really competitive what we have of fossil fuel today. So that's good to have in mind. But also when we are developing the technology, there will come more and more specifications, for example, how to connect to the grid fundamentally, but also how to operate. Should they operate like conventional synchronous generator, or should they just stay connected? We also have a flexibility. We get more and more flexibility with all this storage we are we are putting into the system. Also thanks to the transportation sector, that this is becoming electrified and battery based. We are seeing into a grid structure where a lot of power electronics are connected and will dominate, let's say, the connection. And then we can say, seen from a hardware perspective on this equipment, new devices are coming. They will absolutely give us challenges in terms of having high reliability. In that context, also how to design so it's not disturbing each other. We will see more sophisticated intelligence in diagnostics, control of both the supply and the consumption, for example, to apply AI or what is and what could let's say benefit our mission in general. Power to X, I have been around in my presentation. I see this. I don't believe on a hydrogen-based society. I believe on an electrical-based society. But we need, for part of the whole energy mix, we need to do a transformation into the hydrogen. And then, of course, I see renewables as very competitive today and much more in 10 years. But when I also look at the whole energy system, the needed skills, you can see this is not only electrical engineering. It's also a lot with electronics, but it's also mechanical engineering. It's also the ability to combine electrical engineering and mechanical engineering, mechatronic engineering, because we need actuators, the whole automotive industry, the whole area in terms of wind turbines. We need really many different skilled people in those domains. And yeah, of course, as a backbone, the technology of power electronics, in my opinion, is really a key technology to make a more efficient and a more carbon emission, more likely to obtain a carbon emission-free society. With that, thank you very much for your attention here this morning, and I will be happy to answer questions you might have.
Okay, thank you very much, Professor Blaabjerg, for your interesting presentation. It was a very, very amazing overview of the different applications that power electronics have right now for a modern carbon neutral society. Now we have some time for questions. Tenemos algunos minutos para algunas preguntas. Ustedes pueden plasmarla en el chat. You can write your question in the chat, or you can raise your hand, o pueden levantar también su mano. María Inés, voy a habilitar tu micrófono.
Okay. Hello, good morning.
Hello.
And good afternoon, everyone. Hi, Fred. How are you?
Good. And you?
Good. Fine, fine. It's a little cold. It's not summer like you, but it's nice. It's a nice day here. Very nice talk, Fred, as usual. I want to know your opinion. You like in the sense of storage energy with this renewable. How you see the green hydrogen among the batteries and all the rest? Is really a potential? It's because regarding less than the transmission, okay, you may storage hydrogen and retransform in electrical energy, but here is some people are working on how to let's say transport hydrogen, like also using gas pipelines. Yeah. So it might be very interesting.
Sure. I think this has been discussed in general a lot. How will we see the future mixture? I think we will, and also I think you saw one of the slides. I showed one of the slides where we are building those islands. So I think there are a very big movement towards converting electricity into something which is either capturing CO2 or do something else. So we also have some energy density products. So I see a very big, let's say, market in that direction, but I do not believe on that it is going to take everything, because the efficiency is simply too low, in my opinion. And looking at just, let's say, 20, 30 years ahead, I doubt we will have too much energy supply. So we will not have low cost of electricity. So it will only be and that's a lot. We will see this kind of products coming from the high energy density areas like airplanes, maybe ships, and so on. But in Denmark, they have decided in the last, let's say, half year to increase the offshore wind from 2 gigawatts to 12 gigawatts within 10 years. So from 2 gigawatts to, and all of things should be power to X. This is decided. So this is on the way. But it will not substitute the others. This is really waste of energy. I say, if we have enough, let's say, battery material and so on, we should really stick to electricity into the cars. This is much most efficient.
Okay.
This is this is how I look at it. And then we should try to see if we can make the process of power to X as efficient as it possible.
Okay. Thank you very much.
Thank you, María Inés, for your question. Professor Jorge Pons.
Hi, Frede.
Hi.
Nice to see you.
Nice to see you.
Yeah, very interesting your presentation. It would be interesting to know about your vision concerning risk management of this hydrogen transition process. Because we have, for example, for mining, we have mining situations, gas situation with explosions, fires, and maybe incidents. And then chemical reactions, mechanical and structures stresses in the equipment, and also logistics and human factors. What do you see the main issues concerning improving reliability, safety, and reducing risk in these hydrogen transition systems?
Oh, that's a very good question, and also a difficult question, to be honest. But I have now been working for 10 years in reliability engineering, and I become more and more convinced that, let's say, finding some systematic approach to assess complicated systems, this is very important, and be trained to that. To do risk assessment, also to train engineers, to train ourselves in a very systematic way, to let's say, in a very structured way, to analyze what are the potential things which can happen, what will happen, how can we prevent it's going to happen. I think for me this is a very important approach we should teach ourselves and also our students and so on. And then I think this will help a lot in the overall of the overall systems we are dealing with. And I see this as in many different. I'm not so experienced in mining, unfortunately, but I see this being applied in automotive, in the renewable sector. And if you have this systematic approach, then you can also more easily learn from the negative experience and try to improve the next times when you are doing, let's say, new plants, new products, and so on. So that is maybe, I think this is my best answer I can give to you on a relatively complicated. But so that means systematic system engineering, systematic approach to it, and use this also when it's an operation.
Okay, thank you, Frede.
Thank you very much, Professor Pont. Cesar, give me 1 second now.
Thank you very much, Professor Blaabjerg, for a very nice and comprehensive presentation. I enjoyed it very much, and I'm sure all the students in the audience learn a lot. I had, and thank you, Marco, for organizing also and inviting. I had a couple of questions written down while you were talking, and some of the issues you already touched when replying to Professor Valla. But nonetheless, I think there's some aspects that I still missing. You mentioned the islands that you showed. I had the question: are they actual infrastructure? Or are they being built? Are they ideas, or are they projects? What was the stage of that?
They are being built. They are being built. So it's ongoing, and they will be built in the next 10 years to come. So out in the North Sea, they will build. So far, as they have. European Union has decided, I'm sorry if I'm not 100% accurate, but I think they have decided to build within the next 15 or 20 years around 100 gigawatts of installed capacity in the North Sea. And Denmark is a part of this, and we are just decided to go from 2 gigawatt to 12 gigawatt, and it is decided. It's not something we're just discussing anymore. And this will be a combination of doing this hydrogen products, and maybe even post-processing. So is that you do something with some processes afterwards. And then for some part of it, there will also be electrical connections to other places like shore, Denmark, but also other connections. So this is ongoing, and of course accelerated significantly because of the war we have in Europe.
Right. Related to that, hydrogen has been very much in discussion here in Chile because they're building a pilot plant, etc. But you said something very interesting. I had a question. Is that what do you know about the round trip efficiency of producing hydrogen and back electricity? Of course, there's a place for hydrogen, as you rightly mentioned, but the efficiency is an issue, and you just mentioned it. Could you elaborate a little bit more for the audience, please?
My general statement is that we should only go for hydrogen where it's needed. Where it's not needed, we should not do it, because the efficiency is simply too low. If you go, as I have seen some numbers, if you go from, let's say, electricity and then to hydrogen and then back to let's say if you do a combustion based on, as you do processing and so on, then your efficiency is 15%, as a 1.5. If you go from electricity, maybe through a fuel cell, as a hydrogen fuel cell, then the efficiency is maybe 25 to 30%. While if you go electricity to battery to electricity, then the efficiency is 70 to, let's say, 70% on. So of course, this makes no sense. Maybe it does if the energy is very cheap, but if we do not have enough energy, then it's too costly to go into that direction.
And another question, a little bit related, but perhaps farther from our expertise as an audience, but is nonetheless a concern of mine. You emphasize the usefulness of battery storage, and also Chile has a lot of interest because of lithium, etc.
Yeah.
But what do you know about possible and future recycling of those batteries? Because sure. I've looked at it and I haven't found anything.
Okay, there are activities. We talk also about second life of batteries, and then also reuse. But there's no doubt a lot of programs are being put up in order to be able to reuse the battery technology, and that can limit a little bit the technology itself, because if it has to be reused, and for example, in Europe, there are coming more and more demands on that products you put into the market, you should be able to also take back again. Okay, if you are not able to do this, then you're out. You cannot come into the market. So because we want to have more and more recycling. So in my opinion, maybe the first, let's say, generation of electrical vehicles is not in a very good way able to reuse material, but in my opinion, this will come very fast and be a demand, at least in some areas around the world. And maybe lithium-ion, we are going to see other material which in the future will be found. I believe on scientists that they will find ways out of this.
Thank you very much. Thank you.
Thank you.
Thank you very much, Cesar. Ersan Kavachi, now you can ask.
Hi, Fred, and thank you for your insightful presentation. It was always nice and chanceful for me to listen to you in your presentations. And also, I would like to express my greetings to all present, all attendees. I am attending from Turkey. Yes. And you have been to IT Smart Grid last week, I think. Yes. Yeah. My question is that how do you evaluate the contribution of power electronics to smart grid applications? You know.
Yeah, but for me, the grids will be interfaced by power electronics everywhere, and the power electronics is giving us all kinds of controllability. So when we talk about smart grid, and for me, smart grid is the the option to control where you want to control when you can control where you want, and you can control it when the time is to be done. And for the future grid, the power electronics technology plays both from the generator side, from the consumption side, as well as part of the control of the grid, very important roles, in my opinion.
Yes, and is there any particular control structure or control objective required for integrating power electronic systems to smart grid? You know, smart grid is a phenomena comprised by two-way of power flow and two-way of or bidirectional flow of communication systems. So, do you consider that the power electronic devices should be remotely controlled in smart grid applications?
Absolutely.
We
are building up, in my opinion, a hardware structure based on converters and so on, and then we are also building up a communication network, which let's say will also put references to all our control, to all our hardware. No doubt about this.
Yeah. Okay.
Absolutely. Thank you. My biggest concern is cybersecurity.
Yes, it is a broader
how to keep it, how to keep this safe, and also if it becomes attacked, how to detect attack, and how to let's say still operate if it is attacked heavily. For me, this is one of the. I'm not an expert on that, but that's where I have my very large concern, I would say.
Okay, thank you.
Thank you very much, Ersan. Frede, we have a few more questions in the chat. One is from Yanes. In regard of hydrogen generation, the specific challenges on its storage, transportation, distribution, which is, in your opinion, the main challenge in terms of power electronics?
In terms of power electronics, I would say it depends on the applications. If you go, for example, to the automotive area, some of the figures they tell us things are allowed to cost as a 100 kilowatt converter, maybe $10 or something like that. For me, this is this is one domain. If you go into other domains, if we talk about a wind turbine converter, if we talk about let's say a big power transmission, then I think the challenges are different. So the application will dictate the challenges more than the specific things in respect to it. But there is no doubt that when we talk about technology, reliability, thermal management, protection, this will always be a key in order to have a very robust and a strong technology. And then at the end, if you go into industry, they can only say cost, I guess, or seen from a lifetime perspective.
Great, thank you. We are in the end of the time, but we have a few more questions. How do you see the green hydrogen concerning as a plant dimensions in terms of production and storage?
Well, I think it was a little bit what I discussed with Professor Imex, I see it as an important part of the whole energy mixture, but I do not see it as the dominant part. But I see it as a need, and this has also been realized in many countries that this is a way to, let's say, to have solutions for the energy intensive applications. So this is booming. This is what I see, at least in my place. I have also heard something is going on in Chile. You have areas where you will do some of the same things, as far as I have heard, but I can be wrong informed.
Yeah. Valentina Parra say that it is very different the way of renewable energy are transformed and injected to the transmission network or not? Are there any possibility of transform not renewable energy centers into renewable energy centers, like adapt the system of coal or gas plants to a solar or wind power plant in order to low cost, or let the actual industry to reinvent themselves?
So if I understand this very good question, correct, the question is, I would say a little bit, do we see in front of us a future grid structure, which is like we have already today with big generation centers, if you can say so, aggregated by many smaller units? Or are we seeing a grid where we see it much more distributed and we do not have this aggregation? And I can be wrong on the interpretation of this, but I think it is like this. And what I maybe see for me in the future is a mixture of it. I guess we will see microgrids and microgrid is something which is smaller than the big ones we have here today, as zones, areas which are able to deal with the consumption and production themselves without necessarily being connected to other regions and so on. So this I expect to see because of this transition we are seeing.
Mm-hmm. Okay, thank you very much, Frede. We are almost finishing, and I have just one question. For me, it's very impressive how power electronics applications have increased, and they have played a relevant role for the energy transition and also for a modern carbon neutral society. What do you think is next? Which are the new challenges and trends for the future electronics, mechanical, mechatronics, engineering that they will have?
I think if you look in my expected future energy carrier, where the electricity is going from being 20% to be plus 50% of the whole energy system. For me, what I see of a very big challenge is to create a grid energy system which is all the time able to deliver energy on demand, totally independent on weather or whatsoever will happen. And in order to do that, we need a lot of skills in order to be able to do the production, in order to be able to control the loads, as well, of course, also to do system operation and so on. So and the power electronics is really the technology which makes a lot of, let's say, flexibility. So for me, creating this energy system is a very big challenge in the future.
Okay, thank you very much, Frede, for your time and your presentation. I will speak just a few words in Spanish. La idea de esta charla fue de motivar un poco a los estudiantes del área eléctrica, electrónica, para que se motiven a perfeccionarse aún más y darse cuenta de que existen grandes desafíos aún en nuestra área para contribuir a un mundo mejor, carbono neutral, y también contribuir a mitigar y adaptarse al cambio climático. Frede, in order to finish our presentation for today, I would like to ask you a few more words just to close this meeting.
Okay, I can just maybe continue along the line I have been saying today, that we are looking into a climate challenge which we need to come up with solutions to solve, and we need any kind. The engineers are going to help here. And I would say everybody totally independent on whether it's mechanical, electrical, electronic control, have a responsibility to help us to come up with smart solutions, so we also have a sustainable planet within 100 years. So I hope to see you at conferences and in other places with new ideas.
Great. Thank you very much, Frede. Thank you very much to all the attendees. Let's keep in touch. We will send some email for future activities. Okay.
Sure.
Goodbye, everyone.
Bye-bye. Have a nice day.
Goodbye.